came home. Or
All right.
not home, but over
So-
to my house.
Hold on, guys. All right, so the periodic trend notes. I'm going to kind of go through this briefly. A lot of this you guys can just read and kind of and understand. It's not like there's no secret to a lot of it, but I'm going to try to kind of point out some things. So, names of stuff. Columns. Columns are vertically up and down. Columns on the periodic table are called families or groups. So that's vertically like this. Okay, columns or families or groups. And rows across are referred to as periods. The way I remember it is you read a sentence horizontally, like left to right, you read a sentence and it ends in a period. So that's how I remember that horizontally are called periods. And then families or groups are vertically. Families have similar chemical properties because they have similar valence configuration, valence electrons, the outer ones. So like everything in a family vertically will act similar to each other. A lot of them will react with the same things, stuff like that. Okay. Periods are arranged by increasing atomic number, the number of protons. You guys already know that. Each new period represents the beginning of a new energy level for electrons. You probably don't know that. We'll get into that a little more later. Electron orbital blocks. Again, this isn't going to make a lot of sense right now. This is just the information. There are 4 blocks based on these things called electron orbitals. And let me see if I have that. I think I've got that picture here. Or I did. Where'd it go? So come on. Oh, here we go. These are the electron orbital blocks. The coloring in these. So this is the S block. This is the D block. This is the P block. And this is the F block. So again, just generic idea. Like we're going to go over some of the stuff later. It'll make more sense, but this is just a general information. Okay. All right. Metals, semi-metals, and non-metals. Metals are found on the left and middle of the periodic table. Semi-metals, metalloids, are usually found in the stair step between metals and non-metals. And non-metals can be found on the right side of the periodic table. So the one on the wall, these are metals are in blue, semi-metals or metalloids are in purple, pink are the non-metals. Okay. And then this lists like properties. You guys can read the properties of them. I don't need to go through all of them. Questions on any of that so far? All right, let's flip it. So this is the main thing I want to hit today, is this periodic trend. So the periodic table is actually even more useful than a lot of people realize. Like we know that it's arranged in increasing atomic number. We know that there's like some of the stuff we just talked about, metals, semi-metals, and metalloids are all grouped together, non-metals. We know those type of things, but there's actually other trends in the way they set up the periodic table. So even if you don't know something exactly, you can figure out in relation to other things if it's bigger, smaller, whatever, depending on what you're looking for. So the 3 periodic trends that we're going to look at are atomic radius, ionization energy, and electronegativity. Okay, so let's start with atomic radius. Atomic radius is the distance from the center of the atom's nucleus to its outermost electrons. atomic radius gets larger going from top to bottom on the periodic table. This is due to an increase in energy levels. So let me give you an idea here. That should be fine. Graph paper. Okay. So if we look at like the first column here, hydrogen has one electron, so it's got an electron in the first energy level. Lithium has 3, so lithium has 2 in the first level, 1 in the second level. Sodium has 11. It's got 2 in the first level, it's got 8 in the second level, and 1 in the third level. So see what's happening every time you go down a row? You're gaining enough electrons to start a new energy level. So the distance from the center to the outermost electron is the atomic radius. So each time you add a new energy level, that atomic radius is going to increase, right? That makes sense? Okay. So that's why the atomic radius increases as you go down the periodic table. Okay. Going from left to right, the atomic radius gets smaller. This is due to the increased attraction between protons and electrons as more are added. So if we were to look at, if I were to look at sodium and then magnesium is 2, 8, 2, and then aluminum is 2. You guys can't see that. 2, 8, 3. And remember, each time we gain an electron, as we go left to right, we're gaining protons too, right? So sodium has 11 protons. Magnesium has 12 protons. It's the atomic number. Aluminum has 13 protons, right? So they're not gaining an extra energy level yet. They don't have enough electrons. But what happens is, think of them like magnets. Like protons and electrons attract each other, right? Because they're opposite charge. So they attract. So the more you're adding more protons in the middle as you go left to right, and you're adding more electrons. So it's kind of like adding more magnets. So what's going to happen is you've got more of them, so it's going to have a stronger pull on the electrons. It's going to pull them a little bit closer to the center as you get more. So what happens is left to right, the atomic radius actually shrinks a little. Okay. Questions on that? Okay. So if you look down at the bottom here, this is a periodic table with all 3 trends. You don't need to mark these. That's for something else. The atomic radius trends, as you go from left to right, atomic radius decreases. As you go top to bottom, atomic radius increases. Okay? All right. Ionization energy. The energy needed to remove one of an atom's electrons. So how hard or easy, how much energy do you need to take an electron away? Okay? So ionization energy decreases from top to bottom, goes down. Why? Remember, think of your protons and electrons like magnets, right? So if you're taking away the outermost electron, the further away it is from the nucleus, the easier it is, because the further away it is from those protons that are holding it in, right? The further away a magnet is, the less strong that attraction is. Same thing with the electrons and protons. So this, like this electron, because it's further away from the center, is a lot easier to remove than this electron is, because it's closer. Does that make sense? Okay. Ionization energy, or the amount of energy that you need to remove an electron. So remember, think of it this way. The more energy you need, the harder it is to pull it away, to pull that electron away. Okay, the easier it is, the less energy you need. The amount of energy you need, ionization energy, increases as you move from left to right, except for the noble gases. And this is because the closer the valence electrons are to having a full valence level, the more difficult it is to remove them. So, like, sodium actually really wants to get rid of this electron, because if it gets rid of it, it has a full layer right under it, right? We did that with the ions, right? So if it's got two, I don't know if you guys remember, it was like the octet thing. Like, is it easier to lose 2 or gain 6? Right? It's easier to lose 2. So from left to right, as we go across, they were gaining them, right? And then these over here on the right side don't want to lose, because they're closer to being stable to gain them, right? So like fluorine, way over here, fluorine has 9. So like fluorine has 9 protons, and it's got 2 electrons, and then it's got 7 electrons. Fluorine is so close to being stable. All it needs is 1 more electron. So it's like almost there. The last thing fluorine wants to do is give up an electron, because that makes it even further away. Like, fluorine does not want to give up any electrons. It wants to gain 1 more. It's so close to being stable. So the ionization energy, or the amount of energy that would be required to take away an electron, would be really high for fluorine, because it doesn't want to give it up, so it's holding on to them really tightly. Okay, make sense? Questions on that? Yeah.
Is that kind of part of why fluorine is so reactive, because it's so desperate to get that last
Yep.
electron?
Yeah. Things that are very close to being stable, either by gaining 1 or over here by losing just 1, those are typically the most reactive, because they're so close, which means they will react with anything that will either give up an electron or take an electron, depending on what they want to do. So, they can.
Bonds,
Yeah. But that's still a reaction. Like, yeah, so they're still really reactive. They can share with them.
Yeah, like water molecules.
Yeah. Mm-hmm. Yep. Yeah. So, okay. So ionization energy, left to right, it increases. Top to bottom, it decreases. Okay, electronegativity, the third one. Electronegativity is an atom's ability to attract electrons in a chemical bond. You can think of this sort of as like, how bad does an atom want to gain electrons? Like, the more it wants to gain electrons, the higher its electronegativity is going to be, because it really it's like, trying to pull them from anything it can. So electronegativity is going to be kind of a lot like ionization energy, because as you go left to right, they're getting fuller outer levels, which means they really want to gain electrons when they get over here. Like, just like we said with fluorine, right? Fluorine doesn't want to lose, it really wants to gain. So the electronegativity, the ability to attract electrons for fluorine, is going to be really high. Now, something like sodium, which only has 1, like, it's not going to have a real big, it's trying to get rid of that one. So it's going to have a low electronegativity. It doesn't want to attract more. It wants to get rid of them. So electronegativity is going to be low to high, left to right. And top to bottom, it's going to decrease. Its ability to attract electrons is going to decrease. And the reason it decreases top to bottom is just because you're filling, if it's trying to gain an electron, as you go top to bottom, you're in energy levels further from the nucleus, which means the attraction is weaker, which makes it harder for them to attract it. So it's going to have a lower electronegativity. Okay? Now, so that's kind of the why behind those. I know it's kind of a lot with that. Let's look at actually sort of using those to compare atoms. All right? So what if I asked you calcium and zinc, the ones I have in green here, which one has the bigger atomic radius? And how do you know?
Calcium.
Calcium?
Yeah,
How do you know?
because it's further left on the periodic table.
Yeah, atomic radius decreases left to right. So calcium, so that means zinc is smaller than calcium, right? Okay. What about boron and indium, which has the smaller ionization energy?
Indium.
Yeah, ionization energy gets smaller as you go down. So which one has the smaller one? Indium does. Good. Now, what if I asked you which one, W or Se, has the bigger electronegativity? Okay, so hold on. Let me zoom out a little bit. You need to see both electronegativity. There we go. Okay. Now they're not in the same row or column, right? Like they're not in the same row or they're not in the same column. When that happens, this is what you need to do. You need to find a common atom. So there's two common atoms for every pair like this. So on this one, it would be either PO, because it's in the same column as SE and the same row as W, PO, or CR, because CR is in the same column and the same row as SE. It doesn't matter which one you use. It just has to be one that sort of joins them. And here's how you do it. So I'm going to use the PO. Hold on. Okay. I'm going to use so close. Zoom out a little more. Okay. So I'm going to use the PO. So I'm just going to pick two of them. It doesn't matter which one you start with. I'm going to pick the PO and one of them to compare. So I want, what did I say? Electronegativity. Oh, I haven't written yet. Did I say increase or decrease for electronegativity? Did I not pick one? Let's say, so let's say which one has the bigger electronegativity. Sorry, anyway, really? You guys are getting an example of why I write in all caps. Okay. So bigger electronegativity, Se or W. Okay, so I'm going to use PO. I'm going to look at Se and PO first. Se and PO. Electronegativity. I want the bigger one. So electronegativity decreases as you go down, correct? So I'm using Se and PO. So which one is a bigger electronegativity? Se, because it's higher up. So I'm just going to use the like greater than less than symbols like in math. So Se is bigger than PO. Everybody good so far? Okay, now let's do Se and, or no, I'm sorry. Shoot. Oh, for real. Hold on. Sorry. sorry, not SE. We already used SE. Let's do okay, let's compare W and PO. So we're here and here, and it says electronegativity increases left to right. So which one is bigger? PO. So I'm going to do PO bigger than tungsten W, right? Now, all you need to do is just put these together and then take a look at what you have. So we've got SE, I'm just going to do it over here. SE is bigger than PO, and PO is bigger than W. So if we're comparing SE and W, which one has the bigger electronegativity? SE, because SE is bigger than PO and PO is bigger than W. So SE would be the one that has the bigger electronegativity. That makes sense? Okay. So that's how you do the homework. That's like what you're using with these. Okay. Make sure you look and see if it's talking about like what trend it's talking about, if it's talking about larger or smaller. Make sure you're reading those carefully and correctly. And you're just going to go through and identify on the homework, you're going to go through and identify, like, compare them. Some of them will be in the same row in the same column. Some of them will not. And you'll have to do the kind of intermediary one. All right. Okay. Any questions? Okay. The one more thing. So these two rows at the bottom of the periodic table go in this spot here. Okay. The whole periodic table actually looks like this. The actual full periodic table looks like this. Okay. These two rows right here are what they pull out and put underneath. And the reason they do that is just because if you did it like this, you wouldn't be able to actually have this on a piece of paper and actually see anything that you have written in the squares or anything like that. It's just way too long. Okay. Yeah. Hold on. 23 NP or PO.
Or
NP or PO. So NP. 93. There we go. Okay. NP and PO is here. Yeah. So this is hold on. Let me get the one I wrote on earlier. Oh, shoot. Oh, here we go. Okay. So NP is here, right? And PO is here. So, sorry. There we go. Okay. So these two go in this spot here. So if you were to number the rows down, it'd be like 1, 2, 3, 4, 5, 6, 7. This is like this top one is row 6, and this is row 7 in here. So basically what you have is NP would be down here. So what I would use if I were you, I would use the LV. I would use the LV as the in-between one, because that's in the same row as NP and it's in the same column as PO. Does that make sense?